is kind of putting it all together. I'm going to talk real specifically about what I'm going to expect from you on the test next Tuesday as far as graphs and questions that I want you to answer. And we'll just kind of go through these trig graphs. We're not obviously going to do 15-point values for every trig graph like we did in our sketches, in our graphs that we did on Monday and Tuesday of this week. I'm going to show you kind of a short way to graph any trig function. And today we're going to start transformation of trig graphs, and we'll finish transformations of trig graphs tomorrow. And then by the end of class tomorrow, we'll have finished all of the material for the test next Tuesday. I'm also going to give you a review sheet tomorrow so you can start preparing for that. It would be bad to wait until Monday to prepare for this test, just because a lot of this stuff is foreign. It's not something that you've learned before if you've not had a trig or advanced math class. So trig functions and their graphs, we're going to start with a graph that looks like this. And this is what I want your trig graphs to look like for me. And what you have, or what we did on Monday and Tuesday, was a much more detailed version of this. So, draw a little short y-axis, a couple of hash marks on it, 5 or 6 hash marks on the right, and a couple on the left is good enough for me. We're not going to be real specific about how many periods we graph, how many positive periods, negative periods. We just want to graph a period or two of the function so we know its shape, and then we'll label the graph around it. All right, the information over here on the left, the domain, range, x-intercepts, y-intercepts, and the period of the function. We'll also talk about the amplitude of the function. Those are pieces of information that I could ask you about any trig graph that we're going to look at. Okay? Now, you can use your chart, the chart that we did, the chart that we quizzed on. That's always going to tell you the starting point, right? What's the starting point for the sine graph? The sine of 0 is 0. So we're always going to start there, and then what does the sine do from there? Sine from 0 goes up to 1, right? On your table of values, it's actually 1 at pi over 2. We're not going to label anything just yet, and then it turns around and goes back down to 0. Then it moves into quadrant 3 and goes negative down to -1. Well, that's too low. And then it just bounces back and forth between 0. Right? Y'all watch what I'm doing here. 0 up to 1, back down to 0. Then it goes negative down to -1. And then from -1 back up to 0, and then it starts over. 0 to 1, 1 to 0, 0 down to -1, -1 up to 0. As you go through the quadrants, it changes from positive to negative, negative to positive. Okay? So that's what the one period of the sine function is going to look like. And then it continues to repeat itself over and over. So it would go up to 1 on this side, it would go down to -1 on this side, and back up to 0. So that's what the sine graph looks like every time we graph the sine graph. Every single time it starts at 0 and bounces around between 1 and -1. Okay? I don't like that. That looks a little tall to me. Now let's talk about the domain of the sine graph. Is there any x value that breaks this? Does the sine have any undefined outputs? Look at your table. Sine's not undefined anywhere, so the domain of the sine function is all real values. Any angle you put in it, the sine can handle. Okay, the range, that's the y values. We talked about that yesterday, I think. The range is from, if we use interval notation, -1 up to 1, inclusive. think yesterday we did negative 1 is less than or equal to y is less than or equal to 1. That's the same thing as negative 1 to 1. We jump down to the period. What did we say the period of the sine function was? Period is 2 pi. And the period is the distance between where it starts repeating itself, right? So the period starts at 0 and goes to right here, and then it starts over again. And we're always going to use the period of the sine function to label the axis. So this is 2 pi, right? Half of it would be right here in the middle. That's half of 2 pi is pi. If you half that again, you get pi over 2. This is going to be 3 pi over 2. If we went the other direction, this is negative pi. This is negative pi over 2. This would be 5 pi over 2. And we talked yesterday, I think we got to this point, we talked about the important values are 0, pi over 2, 3 pi over 2, 2 pi, all the odd pi's over 2, and all the whole pi's, right? So what are the x-intercepts of this graph, right? If we just wanted to talk about the x-intercepts, right? Here's 1, here's 1, here's 1, here's 1. There's going to be another one right here. What would it be? 3 pi is correct. Whoever said that. Yeah. All right. So how would you describe these x-intercepts? If I ask you what are the x-intercepts of the sine graph, and I want to know all of them, how would you describe it? That's a problem, right? How would you describe the x-intercepts of the sine graph? Anybody? 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, negative 1 pi, negative 2 pi, negative 3 pi. What are those coefficients called? Integers, right? So we could describe the x-intercepts of the sine graph as all integer multiples of pi, okay? If we wrote it out, the x-intercepts for the sine graph, the x-intercepts, we could say, is all integer multiples of pi. I got to pick up my pace here so we can get to our lesson. Now, math is not going to do that, okay? Math is not going to do, that's not math notation. If it's an open-ended question, that's okay for you to write that. The integer multiples of pi. The mathematical notation for this would be, okay, all k times pi, and then we need to find k to be what? K is an element of the integers. And it's important to be able to read mathematical notation because there's lots of mathematical notation in calculus and basically every math beyond trig. You're going to have a lot of notation stuff to read. All right, so integer multiples of pi, we could write that as k times pi, where k is an element of the integers. Okay, the y-intercept of the sine function is, where's it across the y-axis? 0. 0, 0, right? It's the x and the y-intercept. Okay, calculus students, the maximum and minimum values for the sine function occur at the odd multiples of pi over 2. Pi over 2, 3 pi over 2, 5 pi over 2, those are where the maximum and minimum values occur for the sine function because they are the zeros of the cosine function, which is the derivative of the sine function. Okay? All right. So that's what sine of x always looks like, y'all. Sine x always starts at 0 and bounces between 1 and negative 1. Okay? Cosine x. Cosine x first 6 problems of your homework tonight, sketch the graphs of these functions that we're doing now again. We did on Monday and Tuesday. So just knowing what the parent graphs look like, the basic graphs looks like, is very, very essential before we start talking about a lot of the complicated transformations that we can do to these things. But even the transformed graph of the sine and cosine always looks the same. All right, cosine x. All right, so everybody got at least your graph started here. Y equals cosine x. What's the starting point for cosine? Cosine of 0 is 1, and what do? Down to 0, keeps going down to -1, back up to 0, up to 1, and then it repeats itself. All right, so using the table of values there, we can kind of see that cosine always starts at 1, down to 0. Cosine goes negative in the second quadrant, so it goes down to -1. From there, it bounces back up to 0, back up to 1, and then it's just going to continue that pattern forever. So this is what the cosine graph looks like. Always, the cosine always looks like that. It's an amplitude of 1, so it bounces between +1 and -1. And then we can talk about all these characteristics of the cosine function. What is the domain? Is there anything that causes the cosine to be undefined? Anything that causes cosine to be undefined? Yes or no? No. So nothing breaks it. The domain is everything. The range is going to be all y values between -1 and +1. It's really boring. The range just bounces between -1 and +1. Okay, and we're going to have to label our x-axis to see what the x-intercepts are. And we're going to do that by using the period. What is the distance from here to here? How long before cosine starts repeating itself? What's the period of the cosine function? Look at your graph that we did in class, the detailed one. We went all the way from 0 to what? 360, which is 2 pi. So the period of the cosine function is 2 pi. We can go ahead and write that. Half of 2 pi. If we finish labeling our axis, that's pi. Half of that, pi over 2, which is going to make this 3 pi over 2. Each one of our hash marks is pi over 2, right? So 2 pi over 2, this will be 5 pi over 2. Negative pi over 2. Negative pi. We're going to use the period to label the axis. So the normal period of the sine function is 2 pi. The normal period of the cosine function is also 2 pi. We saw this through discovery, what we did on Monday and Tuesday. All right. X-intercepts. This one's a little bit tougher to describe than the last one, right? So what are my x-intercepts? Looks like I got a negative pi over 2, x-intercepts, negative pi over 2, pi over 2, 3 pi over 2, 5 pi over 2. What would the next one be? 1, 3, 5, 7 pi over 2, 9 pi over 2. So how would you describe that? How would you describe that? What are 1, 3, 5, 7, 9, 11? What are those numbers? Come on, college students. What are they? Odd integers. So all of those x-intercepts are odd multiples of pi over 2. Right? So if I was describing the x-intercepts using words and not mathematical symbols, I would say that the x-intercepts for the cosine function are odd multiples of pi over 2. They all have a reference angle of pi over 2 because the cosine of pi over 2 is 0. So you could look at your table and see the x-intercepts, right? Pi over 2 is 0. So every odd pi over 2 is going to be 0. That's the x-intercept. Here's the x-intercept of the sine function. 0, which is every k pi, right? Pi over 2 here. So what's the symbol going to be? Does anybody know the symbol for odd integer multiples or something? If k is an integer, how would you make it odd? How can you make any integer odd? How can you describe the odd integers? Aren't they the even integers plus 1? All right. 2 plus 1 is 3. 4 plus 1 is 5. All right. So another way there's 2 ways to do this. I'm going to show you the one that you'll see the most, I think. All the integer multiples of pi plus pi over 2, where k is an integer. So if you take your k pi's and then add pi over 2 to it, you're going to get the odd integer multiples of pi. Another way that you could say this, and you'll see this sometimes also, 2k is an even integer, right? If you multiply any integer by 2, it's even. If you take an even number and add 1 to it, and then multiply it by pi over 2, that's another way you could say the even integer multiples of pi over 2. Excuse me, odd integer multiples of pi over 2. What's the y-intercept of the cosine of x? 1. Yes. Man, we're so tired. The whole school is tired. That moon last night felt like somebody left the lights on in the house. It was so bright. Did y'all see the moon? Did you go outside? It was nuts. You could see forever. It's like it was daylight. Once in a blood moon? No, it's a blue moon. We had one of those just a few weeks ago too. All right. So that's cosine x. What do you think we're going to do next? Tangent x. Stick with me. Stick with me. Don't get unstuck. Okay? Tangent of x. Tangent's a little bit more difficult to sketch. You're going to have to kind of do some, it's a little less intuitive. Now we do know that from our table of values, the tangent of 0 is 0. So we got that, right? And what else do we know about the tangent? Look at your table right here on the board. It's undefined where? At every pi over 2. Right, so I got a pi over 2 here. This would be pi. This is 3 pi over 2. This is 2 pi. And that's 5 pi over 2. And that's those odd multiples of pi over 2 again, isn't it? So all my odd multiples of pi over 2, break it. Asymptote lines. Okay? The tangent of 0 is 0. Everywhere we go, the tangent of 0 is 0. So all the k pi's, everywhere the sine of x is equal to 0, look at your table. The sine is 0, the tangent is 0. All right, now what does tangent do? First quadrant, it is positive. Second quadrant, it's negative. Third quadrant, it's positive. Fourth quadrant, it's negative. And then we're back into the first quadrant again. So the tangent just does this over and over and over again. Okay, let's talk about the domain. This one's got some problems, doesn't it? Anything that makes the function undefined is not in the domain of the function, right? So the domain of the tangent function is all real numbers, except, and you could write the word except, here's the mathematical symbol for except. We're going to throw away these values. Which values are we throwing away? All of the odd multiples of pi over 2. So that's k pi plus pi over 2, where k is an integer. Sorry about getting kind of cramped there. Let me erase this so we got room to write that good. Everything except the odd multiples of pi over 2. Everything else works. The range goes up forever and down forever, so the range is all real numbers. The x-intercepts of the tangent function are the same as the x-intercepts for the sine function, right? 0, pi, 2 pi, 3 pi, 4 pi, 5 pi. How do we describe that for sine? All integer multiples of pi over 2. Excuse me, of pi. The y-intercept is 0. And what's the period? This is the width of the tangent function, right? It just repeats itself. The period is pi. Right, 3 pi over 2 minus pi over 2 is 2 pi over 2, which is pi. Okay, that's what the tangent function looks like. We're going to look at one more of these, and then we're going to talk about transformations. I know this is a long class period, but that's what we get for having chapel interruptions yesterday. I'm okay with the interruptions. I'm not against it. I'm just saying we pay for it on Thursday, don't we? All right, number 4 example is going to be the cosecant of x. Which function is the cosecant related to? Sine is the reciprocal of the sine function. So we're actually going to use the sine graph to sketch the graph of the cosecant. All right, did y'all listen? And I showed you this relationship, and we looked at this yesterday, how the cosecant flips the sine. We looked at it on the Desmos. So we're actually going to use the sine function to sketch the graph of the cosecant. So I'm going to start with the sine. What does sine do? Sine of 0 is 0, and then it goes up there and down, and up. Over here, it will go down and up like this. Down again here. I'm going to use it. I'm going to dot it because this is not what I'm trying to graph. I'm just using this to graph the cosecant. This is kind of a framework for the cosecant. Where is the cosecant broken? Where does the cosecant have asymptotes? where sine is equal to 0, right? You can't reciprocate 0, so all of these zeros turn into asymptotes. And then we saw yesterday in Desmos that the cosecant just flips these humps up or down depending on what's going on. So this one will just flip down like this. This one flips up. This one flips down. And this one flips up. Okay. Now, if it's dotted, it's okay for it to stay, but I'm going to erase it just so you were clear that it's just those solid parts, just the things that open down or up that we are going to work with. That's the cosecant graph. Now, the secant, you would graph exactly the same way. Start with the cosine as your skeleton. Everywhere the cosine is 0, that's the x-intercepts, that's where your vertical asymptotes are, and then you flip the humps. All right, what's the domain of this? Let's see, let's put some labels on this. This was 2 pi, right? This is pi. Yeah, because this was cosine, and sine has a period of 2 pi. So this is 0, this is negative pi. This next thing over here, we got 0, 1 pi, 2 pi, 3 pi. The cosecant is broken at all those values. So the domain is everything except k pi, where k is an integer. The integer multiples of pi break it. All right, we're not going to be interested in the range. You can just kind of leave that off. There's no x-intercepts, no y-intercepts. Period is the same as the sine function, 2 pi. Now, these are all testable facts here, all right? But if you can sketch the graph, you can reproduce it. So the first part of the test on Tuesday is going to be sketching these graphs real quickly. So you need to be able to do it quickly. And then can you use the graphs to answer questions? Okay? All right. Secant we're going to leave it for homework. All right? So let's talk now about how we can transform these graphs. 4 ways to transform trig graphs. How can we transform graphs? What do we mean by that? Stretch them, flip them, move them left and right, or move them up and down. Yeah? That's all we can do is move the graphs around. So there's 4 ways to transform the trig graphs, and they're related to these 2 equations. Now, we're not going to deal with transformations of secant, cosecant, cotangent, tangent, other than maybe answering some questions related to it. But the ones that we will sketch graphs of will be sine and cosine. There's 4 ways we can transform the graphs, and there's 4 parameters in these equations. This is not difficult. It looks difficult right now, but we're going to make it simple. As we started off the beginning of this lesson saying that the sine graph always looks the same way. The cosine graph always looks the same way. And that's true even if we're transforming it. Even when we're moving it around or stretching it, it still looks the same. Okay? All right, so it's a matter of knowing it. And these next 4 bullet points you're going to need to memorize. Okay? So put a star here. By Tuesday, you need to know these things. The A value affects the amplitude and orientation of the graph. Okay, the absolute value of A will be the new amplitude. If A is negative, the graph is flipped across the x-axis. Just like the A value of a parabola made it open down instead of opening and up. The graphs are going to go in an opposite direction. We're going to do a negative sine and a negative cosine in just a minute so you can see what these do. Okay, so if A affects the amplitude and orientation of the graph. Absolute value of A is the new amplitude. If A is negative, the graph is flipped across the x-axis. Okay, B changes the period of the function. The period is how often it repeats itself. All right. The new period for sine and cosine will be 2 pi divided by whatever B is. This 2 pi is the normal period of the cosine and sine function. You're going to divide it by B to get the new period of the function if B is not 1. For tangent and cotangent, it would be pi divided by B because the period of tangent and cotangent function are both pi. Because keep in mind that in a trig function, the x is an angle. So if we're multiplying the angle by something, it's going to cause it to grow faster. 2x is going to grow twice as fast as x. So instead of taking 360 degrees to go through the period of the function, if it's 2x, it's going to be 180 degrees to go through it because 2 times 180 is 360. And that's why it's 2 pi or 360 divided by whatever b is. All right? K value, what's K do? Can anybody guess what K is going to do? Nobody wants to. K is going to move the function up or down. Okay, it's vertical shift of the function. So it's going to move the axis of oscillation, and that's the reason that's in kind of quotes there is because that's not a technical word. Normally the trig graphs will oscillate up and down over the x-axis. If we have a K value there, it's going to change. It's going to rotate and oscillate around whatever K is. So the K value is going to shift the function up or down. So we've dealt with A, we've dealt with B, we've dealt with K. What's left? So what's C going to determine? Grammar's writing furiously today. I apologize for the pace we're having to keep here. There's only one thing left, right? We've done orientation, amplitude, period, vertical shift. The only thing left is horizontal shift. B and C actually work together to determine the horizontal shift of the graph. Graph. It's the opposite of C divided by B. Yeah. The horizontal shift will be negative C over B. Tomorrow we will deal with vertical shift and horizontal shift. We're going to look at a few examples right now that deal with amplitude change and period change. And we'll be done. So tomorrow, vertical shift and horizontal shift, sorry. All right, so these facts are important. A is the amplitude of the function. A is the amplitude, the absolute value of A. In other words, the amplitude's always positive. B changes the period of the function. It's 2 pi divided by B. K is the vertical shift. The horizontal shift is negative C over B. Left or right. Those facts you'll have to know and use. A lot of your test questions on Tuesday will just be, what's the horizontal shift of this trig function? What's the period of this trig function? all the way to the final exam, you'll have to know these formulas, okay? All right, so what would y equals 3 times the sine of x look like? Now, you might want to, if you want to kind of, I'm going to work these quickly. Y equals 3 sine of x. What value has been changed here? A, B, C, or K? A, right? What does A affect? The amplitude. What's the amplitude of this function? Amplitude is going to be 3, which means we're going to bounce between 3 and negative 3 instead of 1 and negative 1. So I'm just going to change the way I label the graph. And then the sine is always going to look the same. It starts at 0, goes up to 1, down to 1, negative 1, up to 0, up to, so the sine always looks the same. The period, which is the distance from here to here, is still 2 pi. So this is pi over 2, dividing those. This is 3 pi over 2, etc. And that's what a rough sketch will look like for your test and for your homework tonight. All right? The period is still pi because our b value is 1. 2 pi rather. All right, next example. Y'all ready? Yeah? Cosine of 2x. What parameter has changed on this one? The b value, right? This is going to affect the period. This function is going to have a new period, but we're going to discuss that in just a minute. What does the cosine look like? Always starts at 1, down to 0, down to negative 1, back up to 0, up to 1, and then it just starts doing the same thing over again. So here's what my graph's going to look like. The cosine always looks like this. If you have to graph the cosine function, that's how it looks. The amplitude of this one hasn't changed. It still bounces between 1 and negative 1. The period of this function has changed. The period is now, instead of 2 pi, it's 2 pi divided by this b value. So 2 pi divided by 2 means my period is pi. Okay? Is everybody with me? That means the distance from here to here is pi. Right? Half of that, pi over 2. Half it again, pi over 4. So 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4. The period determines how you label your axis. Okay? And that one's done. That's what I want you to be able to do. Sketch the graphs, label the axis. This one's a little more complicated. If you didn't write those last ones down, you probably need to write this one. Y equals negative 2 sine of x over 2. Well, this one has a couple things going on, right? This one has an amplitude change. It has an orientation change. And it has a period change. Because this is the sine graph, it always starts at 0. Sine of 0 is 0. 0 is neither negative nor positive, so the orientation change doesn't change our starting point, but it is going to change the direction we go. What does the sine normally do from 0? It normally goes up. Because the a value is negative, this sine value is going to go down. This sine graph is, instead of going up here, it's going to go down here. And once it starts, it's bumping around. It's going to go 0, -1, 0. Actually, these aren't negative ones, but down, up, down, up. You just do the same thing over and over. There for that one. So this is what the negative sine graph looks like. Okay. Everybody got it? Now what's the amplitude of this one? It's the absolute value of the A. So the amplitude is 2. So this will be 2. And this is -2. The period is 2 pi divided by the coefficient of x. So it's 2 pi divided by 1/2, which is 4 pi. Period is 4 pi. That means from here to here is 4 pi. Okay, that means this is half of that, 2 pi. This is half again. So we got pi, 2 pi, 3 pi, 4 pi, 5 pi. This is easy to label. -pi. Every hash mark is pi. Okay? I'm going to do this last one really quickly, but just kind of pay attention, and if you needed to fast forward it through the video tonight to see it, you could go to the very end and see this. But this is the negative cosine of 2 pi x. The negative cosine starts a little different, right? Where does the positive cosine start? Cosine of x starts at 1, right? Where's the negative cosine going to start? -1. Everything's opposite. So instead of starting up at 1 and going down, this one's going to start down and go up. Up. Back down to 0. Back down to -1. Back up to 0. Back up over here. So this is what the negative cosine is going to look like. I haven't even talked about the period yet because I don't need to. The graph's going to look like that. I'm just going to use the period to label my axis. The amplitude is still 1, so that's 1 and -1. The period is 2 pi divided by the coefficient of x, which is 2 pi, right? That means the period is 1. 1 radian, about 57 degrees. This one's going to go through a whole cycle in 57 degrees. So from here to where it repeats itself is 1. Halfway there is 1/2. Half of that is 1/4. So we're counting in 1/4 here. 1/2, 1/4, 1/2, 3/4, 1. This would be 5/4, -1/4. This one is labeled in fourths. And that's what that graph's going to look like. That's y equals the cosine of 2 pi x. Negative cosine of 2 pi x. Okay? The cosine always looks the same unless we flip it. That's easy enough. Sine always looks the same unless we flip it. That's easy enough. What's going to change is how we label our axis to adjust for the new amplitude and the new period of the graph. All right? Homework. Got 2 sections here. This is going to be the 6 trig graphs again. Try to do them from memory without looking back at your notes. If you have to look back at your notes, look at your notes. I want you to ignore the domains that they give you. They'll tell you graph it from -4 pi to 4 pi. I want you to graph it the way we just graphed these. That's the way we're going to sketch all our trig graphs. If you needed to extend it, you could. And then 15, 17, 19, and 3-2 is going to be 3 examples just like the ones we just worked in class. Okay?